happen. For the recording, we have homework due Friday and a quiz over the weekend. And so if we're ready to get going, let's do this. Except we should really do this, guys. Okay. Okay. So current. Here. Not chapters 26, chapter 9. Current and resistance. Okay, so let's start out talking about current. Now, I think we have the idea that current is this idea that charge is going to be moving like through a wire, through some medium. And so let's kind of break down what that means. So let's say I have this wire. I can look at a cross-sectional area of this wire, and so we can think of it like this membrane. And then I can think of charges in terms of charges moving through this membrane, where the current, so we have current, is the change in charge over the change in time. So this change in charge is the amount of, let me just say coulombs for the moment. So like not just number of electrons or number of particles, it's the amount of coulombs that pass through this area, that pass through this like cross-sectional area in some amount of time. Okay. So there's a lot here. So let's go through it kind of step by step. First, units. So charge is coulombs, time is second. So we actually measure current in terms of amperes. So like an amp would be a short for an ampere, and an ampere is really a coulomb per second. And you usually just do a capital A for ampere. Given the lack of little arrows on top of here, I'm hoping that you guys get that this is a scalar quantity. And let's talk about that for a second. Because current is kind of like time, where you kind of want to call time a vector because you can think of time going forward or time going backwards, right? So you want to be like, well, there's a direction to it. But if you remember in 220, we didn't call time a vector, we called it a scalar, where if you're adding time, you're going to the future, and if you're subtracting time, you're going to the past. And we justified that by saying, well, yes, you can go forwards and backwards, but you can never like take a left turn with time. So it's not really a vector because more or less is not a direction. It's not like northwest. And we're going to have the same thing with this current. You can definitely think of current like moving to the left through the wire or moving to the right through the wire. But it's never going to take a left turn off of the wire. So it's constrained to that one-dimensional line where it can go forwards or backwards along that line. Does that make sense? Okay. Okay, so in that way, your current can be negative and it can be positive, but you wouldn't put a direction on it. Okay. Next thing, you notice in this toy picture that I've drawn, I have positive charges moving. Is that the reality of what actually happens inside a metal substance? No, right? Because what really moves inside of a metal substance? The electrons, right? The negative charge. I actually don't have a citation for this, but I'm pretty sure that this is just a convention set by Benjamin Franklin. So we say that positive charges carry current, or current is in the direction that a positive charge would go. Not actually true, but let's talk about why it doesn't matter in the least. When we're talking about this change in charge, remember, like, our current is change in charge over change in time. What we really mean is that if I have this membrane here and I start off with 4 positive charges over here, and I end up with 4 positive charges over here, because presumably the charges have moved from the left to the right, my change in charge is 4. Sound okay? Now let me ask you, if instead of that question, I had said, well, I actually had 4 negative charges that started off on the right, and they ended up on the left, what, just looking at the blue charges, by the way, don't ignore the black charges for a second. What change in total charge from right to left would have happened? And so what I'm saying is, for the black charges, I've had to add +4 to the right-hand side and subtract 4 from the left-hand side. Okay. For the blue charges, to go from -4 here to 0, I've had to add 4 to the right-hand side, and then went from 0 to -4, and subtract 4 from the left-hand side. So in both cases, I'm adding 4 to the right-hand side and subtracting 4 from the left-hand side. Does that make sense? I don't like that. I like that. It's minus. So we're talking about how current, we say that positive charges carry current. What we don't mean like the positive charges are carrying current. We're saying the direction that we're going to call positive is the direction where positive charges would flow if they are the ones flowing. And we're saying negative charges move one way is the same as positive charges moving the other. Does that make sense? And if it makes sense, let's take a look at something that we definitely hand waved last week, which is current going through a capacitor. So last week we talked about current just going through a capacitor. But before we did that, we said, I have these 2 plates and I'm putting an insulator in between them. So current is not actually going through that capacitor, right? So one thing we actually know is there's not like charges over here that are going through there. Charges can collect on either plate, but they can't go from plate to plate. Okay, and so let's talk about what's really happening. What's really happening is we have a positive voltage here, and I'll call it a negative voltage, but it could be like a 0 voltage over there. And so this whole wire, it's full of positive charges because it's a metal, or it's a substance as a whole, and substances are made out of protons and neutrons and electrons. So before you hook up the wire, this whole thing has positive and negative charges just floating around, right? Yeah, but yeah, I mean, before we hook up the battery, there's no reason for them to move around. And then we hook up this battery and we say, okay, what's going to happen? Well, what's going to happen is all the negative charges want to go from low potentials to high potentials, right? So all the negative charges, they want to run up the potential hill. And so, am I saying this right? I'm going to say this right. And so what we're going to see is all these negative charges start to move off one side of the plate around to the other side of the plate. Does that make sense? And after some amount of time, what we're really going to see is that all these negative charges are going to start collecting over here. And so one of our plates will have positive charges without negative charges. So it will look like positive charges collected. And the other plate, we're going to have all these negative charges. So all our negative charges collected on that side. And so again, we'll have what we talked about last week, where one of the plates will be positively charged and one of the plates will be negatively charged. Our voltage will eventually equal the voltage of the battery, and we'll have our electric field in there. But it's not because current went through the capacitor. It's because negative charges came off the positive side and went to the negative side. Okay? And the convention, so that's what's literally happening. Electrons are moving off this plate and going towards that plate. What the convention would tell us is that we have a current going around like that. Because if the negative charges are moving around clockwise, the currents that we're defining as delta Q over delta T would be going around counterclockwise. Would anybody like to say anything about that?
So,
yeah.
Even though the electrons are going this way,
yes.
It's the opposite because it's a positive charge?
Yeah. Okay. So because whoever decided that electrons should be negative instead of positive, and whoever decided that current should move in the positive direction, they got their wires crossed.
Oh, it's not like.
Yes. No, it's not based in reality.
Okay, so it's like,
yeah, it's just, basically we're like, okay, this is the way current should go. And then when they started naming the electrons and protons, they said, okay, well, we'll make electrons negative. Or no, like there's nothing negative about it. It's just you had to choose two things, so they chose positive and negative. Okay, is that everyone kind of happy with this concept? So convention-wise, just go ahead with positive charges are moving, and realize that no, it's not reality. Okay, that's good. Next thing I want to look at is this equation. So you guys are probably looking at that equation and saying, whenever you see some like delta over delta T, we're clearly going to start talking about derivatives, because that's change in charge over change in time. And so as delta T gets smaller and smaller, instead of deltas, we're going to deal with D's. And so we can look at delta Q over delta T. This is going to go to the derivative of charge with respect to time, which will be our more instantaneous value of current. And what we're going to find in various situations is we're going to find that current is not so much a steady state, but it changes over time. And so seeing derivatives is going to be really useful. And with that, let's do a homework problem. Which, yes, for chapter 9. So let's look at number 2. Where number 2 has, I like this because we're gonna do a problem. We're gonna see where this shows up in the next chapter. But for now, let's kind of get used to the equations. So we're gonna look at a graph of current with respect to time. I really don't need to so much, but so current with respect to time. Over some circuits, we have some circuit that I'm not going to tell you about. Looks, I turn it on, and the current starts at 0 and then ramps up. First off, if you look at this graph, can you think of what function that might be that looks kind of like that? I like a logarithm back there because it's not a logarithm, but it's an exponential, so it's like an inverse logarithm. And they give it. They say, okay, this current is going to be Imax, where Imax is that right there. 1 minus e to the negative t over tau. Let me write that in the next page. Next, I to the t. Imax, e1 minus e to the negative t over tau. Where? That's a tau on the bottom. Where tau is a constant that we're going to call like a time constant. And when you think of that time constant tau, you should think about things like carbon dating. Have you guys done like radioactive carbon dating, right? Where like every half-life you divide the number of radioactive elements by a half, and you end up with that exponential curve, right? Where the time constant, or the half-life, tells you how steep that curve will be, right? So a short half-life plunges like really close to 0 before leveling off a little bit, and a long half-life gives you a much more shallow curve. Okay, this is the same thing, where this half-life will tell you how steep your curve is going to go towards Imax, whether you like jump up to Imax almost immediately or if it takes a long amount of time. Sound okay? Okay. They're also going to give us Imax, just, to be able to give us a number. And okay, and what we're going to find out is we are going to find out what is the time in seconds. So we want the time in seconds. By the way, that's how I want to see the unknown. Like, what do we want to find out? We want to find our time, and I want the units in seconds. Where the current will equal 75% of the maximum current. Is that all right? Okay, so just looking at this, what that means is, let me just eyeball it, like that's 3/4 of the way up, right? So that's like 0.75 Imax. We're looking for that time. Sound okay? Okay. And this part of the problem, really straightforward. We're gonna put over here 0.75 Imax, and then we're gonna solve this for t. Sound reasonable? So initially we're just going to solve an equation because we know how to do that. Max 1 minus e to the negative t over tau. The Imaxes, what can I do with the Imaxes? Yeah, excellent, excellent. So we have 0.75, 1 minus e to the negative t over tau. So I'll move this to one side. And what is 1 minus 0.75? 0.25, excellent. And then if I want to get rid of that e, how do you get rid of an e? You do, you take a natural log of both sides. And so you'll have a negative t over tau equals the natural log of 0.25. They do, yeah. And it's important to note, it's just a constant, right? So it's not like a time you would have to solve for. Natural log 0.25, 1/4. Like that. And then you just plug in your numbers. And just so you know, when you take a natural log of something less than 1, it's going to be -2. So that's your minus sign is going to cancel out nicely as well. So yeah, this is.
Wait, so it's always, you said it's always -2 if it's less than 1?
Yeah, the natural log of anything like less than 1 will give you a negative answer. So yeah, whatever this is, your minus signs are going to cancel out, and you'll end up with like a 2.1 units of seconds. That should be a t and not a 4. Okay, that made sense?
You're just plugging in, but you're getting set that percent, right?
Yeah, so we just had an equation. We said, okay, find the x for some y. Now we will actually do something fancy, where we want to know how much charge in coulombs. So we need to know charge in coulombs passes through a point in the circuit for as the current increases from 0 to 0.75. So as we go from t equals 0 to 2.1 seconds, how much current passes through this circuit? Does that make sense? Okay. So given that current is the derivative of charge, if we want to know how much charge is passing through the circuit, I have a charge with respect to time graph. Am I looking, and anytime I have a graph, you should be saying we're either going to find the slope or we're going to find the area under the curve. If I want charge, do I want the slope or do I want the area under the curve? Area under the curve. Because if current is the derivative of charge, charge is the integral of current. And so I'm looking for that area. Okay. Okay, let's look at it. So I have delta Q integral I dt. This is I max 1 minus e to the negative t over tau dt. I'll talk about the limits on this integral in just a second. But let's split it up. Well, first off, Imax. Is Imax a constant or a variable? Constant, yeah, because it's the maximum value. It's not going to change. So I can put that kind of by itself. And then I can say, well, if I take away Imax, I'm integrating 1 dt. So I'll just have like dt there. And then I'm subtracting off this e to the negative t over tau dt. Like that. So far, so good. I hope so. What is the integral of dt?
Is it 0 until 2.1?
0. Oh, no. Okay, I like that. So you're very correctly throwing in the limits, right? And yeah, then when you integrate dt, you get t from 0 to 2.1. Okay. Hi, Max. 0 to 2.1 t. What about this second second integral? We have e to the negative t over tau. I can't do that one in my head. I know like what's the integral of just e to the x?
Or is it 1?
No, easier than that. Integral of e to the x.
Oh, it's just equal.
Yeah, just e to the x.
Oh, yeah.
So yeah, I know we're gonna get like e to the something, but now with that negative t over tau, there's
negative t times. Yeah. That's usually there's a constant.
I believe it'd be like negative tau or one of but well we're gonna just do this, guys. We're gonna say that u equals negative t over tau, like that, because I know what the integral of e to the u is. And if u is negative t over tau, what's du going to be? Negative 1 over tau, or in this fact, negative dt over tau. So we can, from there, we can say, well, dt really equals negative tau du. And so that there's our constant. So now we have e to the u, and we want to say du, so we need to say negative t du. Okay, negative tau du. Okay, and you guys correctly told me that the integral of e to the x is e to the x. So this is just e to the u here. And then we have to substitute back in. This is negative tau e to the negative t over tau. Okay. So yeah, so there's our integral, nicely done out. Okay, I got that. I got all. Okay, that's beautiful. I like it. And now we can just go ahead and plug in numbers. We're going from 2.1 to 0 seconds. Our tau was 1.5 seconds. Our Imax was 15 amps. So we can just plug in our numbers. It's not a big deal. Although I will plug in numbers on the next page. So Imax 15 amps. Uh, 2.1 seconds minus 0. I can cancel out these minus signs for my e's. So I have plus 1.5 seconds times e to the negative 2.1 seconds over 1.5 seconds minus e to the negative 0. What is e to the 0? 1. Perfect. Just like everything else to the 0, right? Okay, I think this all looks pretty good. And at this point, you're plugging into your calculator, and hopefully you get something close to 14. Okay, and what sort of units should go on that? I like C, because they're coulombs, right? We were solving for charge. Okay. Did that make sense? Excellent, excellent. Kind of get used to exponentials. We're gonna be doing some next week. Okay, back to physics though. Back to physics. We're going back to this model here, and I want to talk about more reality stuff where these charges are moving through that area. Now, you guys have correctly identified that really what's going on is that negative charges are moving that way. Great. But let's break that down, what we mean by change in charge. Because change in charge, one, we mean net charge. So if for some reason I do have a positive charge carrier, where maybe in this scenario, one positive charge carrier moves to the right and a negative charge carrier moves to the left, what's the net change in charge in this case if I have a positive carrier moving one direction and a negative carrier moving the other direction? Both of magnitude 1 Coulomb. Say again? Other way.
They're both 1.
Yeah, if they're both 1. If I have plus 1 Coulomb moving one way and negative 1 Coulomb moving the other way, what will be my net change in charge going through that membrane? 2.
Yeah, there's 2 charge going.
Right? 2 coulombs. Okay, so I say this not only to say, okay, be aware that you're taking the net total effect here, but also there are actually positive charge carriers. We are not going to talk about them for another couple weeks, but there are different types of charge carriers. So you do have to think about what sort of material you have, because you might have a sort of material like a semiconductor where the charge carriers get very weird. Yeah.
So is the net charge 2 because one's a photon, one's an electron, so it's not incancellable? If they're both electrons, would it net charge be 0?
Yeah. So basically think about, so if this is the before picture, the after picture, you'd have a -1 over here and a plus over here. So like from this side, you went from initially having -1 to the final having +1. So the charge was plus, the change was +2.
But that wouldn't be the case.
Yeah, if they were both negative flipping, you start with -1 and end with -1. So yeah, no change. Okay, so where was, okay, so if I want to think about this net change of charge, one, I think of the charge of the carrier. So like for an electron, that would be the charge of an electron. For a positron, that would be a charge of a positron. So you really do have to think about what those things are. Next thing, you might think about the number of carriers. So like how many charges are moving through. Then you want to think about the cross-sectional area. So that's this area right here. That's A. And then you might need to look at the length of the wire. So you might be looking at like a chunk of wire that you want to examine. So you might kind of cut yourself out a cylinder like this, where that would be delta X. Okay. Sound reasonable so far? Maybe. Okay. With this, what you use this idea for is you use this idea for looking at kind of drift velocities. So when you have a wire and you have current, and you say you put, one side, I'm going to make this current pause, no, I'll make it negative. And you put one side at, a high voltage and the other at a low voltage. That is going to exert a force on this charge to go this way. But of course, we run into reality where that electron cannot actually go through the proton. So instead of going through the proton, it bounces around. It hits this and it bounces out. It maybe runs into the side there. And again, there's a force trying to make it go this way, so it'll bounce that way, but it hits something else and it bounces out, and again, it'll keep trying to bounce its way down. But you should think about this very much like kind of like a pinball machine where the ball wants to roll down, but there's a lot of obstacles, so it will get bounced around a lot as it rolls down. Make sense? And so what that will give you is a drift velocity, where a drift velocity isn't how fast this thing can move. So like along this line right here, it'll have some actual velocity. Like that ball in the pinball machine, it can move very quickly. But the drift velocity is how fast can it make it from one end of this wire to another. So even though the pinball might be moving very quickly, it'll take several seconds for it to get down to the bottom of your pinball machine, because you know it's going to get bounced around in there. Does that make sense? And so that's this drift velocity. And there's actually a lot that goes into drift velocity. Like that's a whole field of engineering in itself is hey, I need to characterize drift velocities of different materials. But for us, let's just like think about it as the actual velocity of a charge moving through a densely populated area. What that means is that in terms of this delta x here, or delta x, that'll be how far a charge can go in some amount of time. So this is like a distance equals rate times time sort of thing. Everyone good? Okay, distance equals rate times time. Now, looking at that, we can take that distance equals rate times time idea back here, and we can plug it into our delta Q. In particular, we can say, well, if current equals delta Q over delta T, and Q is this number of carriers, cross-sectional area, and now instead of delta X, drift velocity times time, all multiplied by the charge of one carrier. My delta T stays down there, and I'm hoping you see that we're going to cancel these delta T's out. Okay, and what that's going to leave us with is this guy, which what this equation gives you is if I tell you I have a copper wire of a certain diameter and a certain diameter, and that's actually it. If I have a copper wire of a certain diameter, you can tell me how much current I can put across it, because you can look up like the density of electrons in copper, and you can look up the charge of an electron, and you can look up the drift velocity per voltage in copper. And then that way, that'll give you an idea of what sort of current that wire is capable of carrying. Does that make sense? Okay, good. Now let's talk about why current might not work. So the next thing to look at is resistance. where this idea right here, this is where resistance comes from. So looking at this, if I had a whole bunch of big blocky nuclei running around in there, is that going to increase my drift velocity or decrease my drift velocity? Decrease, right? Because the more objects that these electrons have to get around, the less fast they're going to make it to the bottom of this wire. Okay, that's where resistance is going to come from. So resistance is this idea that some materials inherently have more blockages than other materials. Okay. So the resistance of something is down to the types of materials at a very atomic sort of level. Like what pattern, what shape, geometric shape. What is that word? The shape that molecules make? I am not. I'm. That one's not gonna show up. That's a graduate level materials class that I'm never getting back. Okay. Types of materials. Okay, resistance. Types of materials. Okay, but we're not going there. We're going to do a little more high level. So let's talk about how current's getting through our circuit anyway. So I have my circuit here with the battery, and let's say I've just flipped the switch. Okay, it just turns on right now. So I have a positive and a negative side to this battery. Now, given that there is a positive and a negative side, I should have an electric field, right? An electric field that goes from the positive direction to the negative direction. But this is a wire. Can I have an electric field inside of a perfectly conducting wire? Nope, I like the no. Because remember, there's a reason for that. It's not that you can dump a bunch of charge on something. It's that as soon as you dump the charge on it, it would spread out to try to cancel out that field. So that means immediately after I turn this thing on, charge is going to start flowing through this to try to cancel out that electric field. So this is like an electric field. So charge is going to start flowing. And it's going to do it under the influence of that force. Force equals charge times electric field. As soon as I turn this on, the electric field will exist for a very short amount of time. And all the charges are going to feel a force to start moving around to cancel it out. And since force equals mass times acceleration, they will be accelerating to do this. So they're going to move faster and faster and faster to cancel this out. Given the picture that I've drawn here, is this a very sustainable picture? So in other words, I've turned this field on. I'm accelerating those particles. When's it going to stop? Never. I have not put a mechanism here to stop the acceleration, which is bad because acceleration is not the same as velocity, right? Velocity, they'd be going at a constant rate, but here they're going to be going faster and faster and faster and faster. So more and more and more energy. What happens when you put one wire across a battery? It sparks. It heats up, right? You guys might have wrapped a battery in tinfoil before. Yes, and the tinfoil heats up, right? That's a fire hazard.
I'm gonna do that.
In lab, we're doing it this week in lab. Yes, you got to make little sparks. It's very nice. Yeah, it totally will.
Fires in lab today?
Yeah.
So what I'm trying to say is that he can set the fire alarm off.
legally, we're just making a tiny little bomb.
So if you were very ambitious, you'd sit there at your lab table and you'd cut 100 tiny little slivers of aluminum foil, and then you might be able to make a small amount of smoke.
Well, I'm very ambitious.
Or you could just get the lab done and go home. Your choice. But I have yet to be even able to char the table, so yeah.
I watched Breaking Bad, so I think I know what
I purposefully did not get any steel wool for the lab, so. Okay, so this is a bad idea. By the way, this is known as a short circuit. And anytime you hear of a short, have you guys ever said, oh my gosh, I shorted something or other? That basically meant you turned it off very quickly, because what you did was you hooked up a positive voltage to ground usually. A bunch of current went through there until you blew a fuse or something. Okay, so given we don't want this situation, we tend to put resistors in our circuits. And resistors are just anything that resists current. So like some type of insulator, it's usually not even like super insulating, but just something that won't transmit current at such a high level that copper will. Okay, so what happens here is you flip the switch, the electric field turns on, the particles start accelerating, but then they hit this resistor. And this resistor is a type of material that is much more densely packed, or has some physical mechanism that it makes charge difficult to get through. So your little electrons will have trouble, getting through this. It'll take them a longer amount of time. And this starts kind of like a traffic jam sort of scenario, where this guy's still trying to get through, and the next little charge approaches and it sees this electron, and at some point it's like, you know what, there's more negative charge ahead of me than there's positive voltage ahead of me, and so I want to stop. And so you kind of get this backlog of, okay, we actually, this resistor, sorry, let me, if I have my electric field here, I have this electric force trying to push them this way, but then I have my resistor with the resistive force pushing them back. And this, it'll take nanoseconds. This isn't like a thing that you're gonna measure. But at some point you'll hit this steady state where the net force equals 0. And so the amount of charge getting through your circuit becomes more constant. So it says, okay, well, I can get, however many charge through this resistor per unit time. That's how much charge I'm going to send out per unit time. Sound okay? Okay, cool. Excellent. So steady states. And that is when your current starts to stabilize, become constant. And you're really never, and I do want to emphasize this, you're really never going to see the point before steady state, unless you do some really, really like not out there research, but specific research. Like it takes some really specific research to look before you hit steady state. It's just not something that you look at. Okay, so what we want to talk about in this situation is we want to talk about the voltage. You either want to say like the voltage of the battery or the voltage across the circuit. Like the voltage across the circuit is a little more general. And we want to talk about what sort of resistor we have. And we want to talk about what sort of current we have in the circuit. And so this is what's going to bring us to Ohm's law. Okay, where Ohm's law relates this V to the I and the R. So let's say I have some sort of voltage across this circuit. If I increase my voltage, do you think I'm going to increase or decrease my current? Increase, yeah. So the bigger the voltage, the bigger that electric field, the bigger that electric force, the more charge you're going to be able to push through that circuit. So our voltage and our current are going to be directly proportional. What about the resistance? If I have a resistor in there, so I have a certain amount of voltage, and I have like, if I have a bigger resistor, do you think I'm going to have a bigger current or a smaller current? Smaller. Okay, so my current and my resistance are going to be inversely proportional. And so generally you write this as V equals IR, where the bigger the current, the bigger the voltage, the more the current. But if you're given a certain amount of voltage, if you increase your resistance, you're going to decrease your current. And if you decrease your resistance, you're going to increase your current. Okay. Things we need to talk about here. One is I introduced this whole R resistance. So R is a resistor, and it's measured in ohms, which you use that Greek letter omega for. What to tell you about this? 1 ohm is 1 volt per 1 amp. Basically, it's just make sure this works. And generally, what you see from this, you see something called, what people talk about is something called ohmic behavior. Where ohmic behavior is just when your circuit is obeying Ohm's law. Okay, and you might say, well, doesn't everything obey Ohm's law? But let's talk about this. And we're going to jump into, I don't know if we're going to get to it all the way. Let's talk a little bit about temperature dependence. I think on Thursday we'll really talk about temperature dependence. I think it was this class we were talking about heat the other day.
Yeah.
Okay, and we said heat was like kinetic energy, right? So heat is literally movement. So when something's heating up, what you're saying is the atoms and electrons inside of that thing are moving a lot more. Okay, we have just defined how something is able to move through a wire as how easily it can get past these obstacles. Okay. Imagine for a second you're in a room full of 2-year-olds. And it is nap time. How easy it is, and they actually are sleeping. They're good 2-year-olds. How easy it is to get from one end of that room to another. Yeah, you got to be careful. Don't wake up the toddlers, but you can make it through, right? That would be a cool, low temperature sort of thing because everything is not moving. Now you wake up the toddlers and you all give them a piece of cake. Wait 5 minutes, they are now moving around, right? How easy is it to move through that room? Yeah, much more difficult because now not only do you have the same amount of obstacles, they're moving around, they're covering more space. So if I say that I heated something up, something became warm, do you think its resistance would be constant or would it change? Change. So if I made something warm, but the temperature went up, what would happen to the resistance? Increase. Awesome. And we'll discuss this later, but let's look at a situation such as a light bulb. and like an old school light bulb with the filament and everything. So I have a light bulb where, whoosh, looks like that. When it's off, is it hot or cold? Cold. Okay, so off, cold. And so when you just turn it on, it's still probably a little cool, right? But after you leave it on for a minute or two, after on for a while, what is its temperature then? Hot. Excellent. So between leaving it off and then you turn it on and then you leave it for a little while, the temperature increases, which, as you guys correctly told me, that means the resistance is going to increase as well. So if the resistance increases, I'm not going to have a really pretty, like, just constant current situation, right? So for R being constant, I put a battery across some object, and I will see, you know, I put more voltage, I get more current in a very linear sort of way, where the slope of this line, is actually 1 over R. 1 over R. Yeah, but it would be a straight line because my R would be constant. But then I have something like that light bulb, where over time, this is temperature dependent, my IV curve will actually start looking like that. Where, you know, when it's cool, fine, it'll work, no problem. It looks the same. But then I put more and more voltage across it, it heats up. It heats up, my resistance increases, and my current cannot increase as much. So this is non-ohmic behavior. And that's what people, if you ever hear it, and you will, if you ever hear like this is ohmic versus non-ohmic, what they're saying is the resistance constant or does it change with respect to time? Time or voltage really. So straight IV curves means your ohmic behavior, non like actual curves when you're looking at an IV characterization, it's going to bend one way or another. Okay, everyone looks pretty happy with that. Okay, I don't actually want to. Do I? Okay, here's what, you know. Okay, I do. Let's go ahead and do this. So let's talk about how you would characterize this. So we have this idea. We have our toddlers, right? So we have a room full of excitable toddlers, which is actually a really, really great way of thinking about this problem. I want an equation of resistance with respect to temperature. So I want to say, okay, I give the kids one piece of cake. I want to measure the difficulty of how hard it is to get across that room. I give the kids 2 pieces of cake. How hard is it to get across that room? 3 pieces of cake, etc. How would you figure that out? If I gave you a room full of toddlers and a cake, how would you figure that out? Okay, I could measure the speed of the toddlers per unit cake. Okay. Do you think it would be very constant? So like I give them 1 piece of cake, right? Like that'll definitely change it. 2 pieces of cake, maybe I'll get like a similar increase. What about the 3rd piece of cake?
Is it like exponential?
It's
the opposite where it's like
I actually like this. We don't know, right? And the idea is not even every toddler is going to behave the same way. So this is a problem with a lot of variables. Too many variables to even want to measure. And whenever you have too much stuff that we don't want to measure down to the minutia, we start approximating. So we start using Taylor series. You guys remember Taylor series? We did it for a whole half hour last semester. So we looked at Taylor series in mechanics when we wanted to talk about air resistance. And air resistance was another problem that was too complicated to really like measure every variable separately. And so instead of saying, I know that my resistance is just a property of this, so just a property of that, I said, okay, let's just say my resistance, which let me talk for a second before I tell you what all this means. There's like some base resistance, but then my next thing, I'll have my base resistance and I'll multiply it by some factor. And then I'll have the base resistance and I'll multiply it by some factor squared. And I'll keep, to the third power, fourth power, however many powers I need. And then I'll go back and say, okay, well, do I really need like the fourth power? Do I really need the third power? Maybe I just need like the first power. And that's in fact what we're going to do. We're going to say, okay, I'm really only going to take the first power. And just so you know, you might find yourself with a material that you need the higher order powers.
How do you decide that?
You do an experiment and you say, okay, wow, I'm using this circuit and it's not behaving the way I want it to, and maybe the temperature has a effect more than what I'm seeing. This is pretty well accepted. Like there's not too many situations you're gonna have more than the first power. And yeah.
In our case, since the first power, we can be doing what specific
what we would so what this would assume for the toddlers is that for every piece of cake you give them, their activity increases by a set amount. So that would be the first order approximation. Okay, given all of that, let's talk about what this is. Because you notice I didn't put R's in here, I put the Greek letter rho. This is something that we're going to call resistivity. And the idea behind resistivity is we want to think about not just each separate wire, like I don't want to think about resistor 1 versus resistor 2 versus resistor 3. I want to think about copper or aluminum. So instead of having a lot of different factors go into my resistance, I'm going to have the resistivity like of a material. And so that's generally what we think, what we think about temperature dependence. It's got units of ohms times meters, and we will discuss this next Thursday. What's going to go inside this parentheses is we're going to have a delta T. So there's our temperature dependence. We're also going to multiply this by an alpha. Okay, so what this means is that this is like the resistivity of something at a base temperature. So resistivity at, I haven't looked this up, but I'd bet strong money at it, standard temperature and pressure. So like the resistivity at room temp. And then here's this term that will tell us how much the resistance will increase if you go up by some delta T. Increase from STP. Okay, where alpha, this is kind of a silly definition. Alpha, you notice, is exactly what you would expect. So if this thing is delta rho, alpha, out, we just solved for alpha there. But this is known as the temperature coefficient of resistivity. And this is a property that you look up again. So you look up the alpha for copper or the alpha for aluminum. Okay. So first off, does that sound okay? Okay, so this is resistivity with respect to temperature. You can write a similar equation for resistance, where we'd have the resistance of one particular object is the resistance at standard temperature and pressure, plus that resistance times alpha times delta T, where this is still, you need to connect this alpha to whatever your resistor is. Okay. Okay, and so at this point, I'm about to call it, but I do want to point out where we're going to go, because we're going to start on Thursday with number 14, so I don't forget. We're not, number 14 is what this problem is. We have some object. It doesn't tell us what kind of object, but it says, okay, I have this resistivity, rho naught plus rho naught alpha delta T. And then they tell us, that the alpha of this particular substance is -3. 9.5 times 10 to the -3, 1 over coulombs. And it gives us a resistivity and a T naught as well. And then it'll ask for, we're going to increase the temperature, and we're going to talk about how that affects this. And so I am actually going to call it right now, but could you guys remind me to go over the difference between Fahrenheit, Celsius, and Kelvin as soon as we start next time, because we're going to be in either Celsius or Kelvin, and we'll need to talk about that.
Isn't it just a conversion factor, or is there something?
It is just a conversion factor, but we need to make sure that which one we're using and how we just don't want to talk about Fahrenheit, basically. Kelvin is really nice, although I think a lot of this is based in Celsius, which makes it just like a touch confusing. Okay, I'm good though. Talk Thursday. Are you guys online okay? Okay, sweet. Have a great afternoon then, and I will see you Thursday. Have fun in lab.